Okay, so we can view our next topic as reversible adiabatic processes. As you can see, what is a reversible adiabatic process? Let's understand what is a reversible adiabatic process. So there are two things that you need to remember while in adiabatic process. One is del Q is 0. There is no heat is added or subtracted from the system for an adiabatic process. That makes it an adiabatic process very fast. Okay, so adiabatic process is very fast. There is no time for an heat exchange. And the next thing that you need to understand in an adiabatic process is that pressure, volume and temperature, these three parameters vary simultaneously in an adiabatic process, unlike an isothermal or an isochoric process. In an isothermal process, temperature is constant. In an isochoric process, pressure is constant. Or in the constant volume process, as the name suggests, volume is constant. But whereas for an for an adiabatic process, reversible adiabatic process, these three vary as well. So your del P not equal to 0, del V not equal to 0, and del T not equal to 0. Please remember this. So how do we represent graphically an adiabatic process? Let's understand that. And just spend some time which will introduce you to some key concepts. So if you just note it down, you can always pause the video because this is a video and note it down. So I'll just move up ahead. Fine. So for a reversible adiabatic process, let's see what is an adiabatic process and how it is different from isothermal process. So this is a PV diagram. These are the isothermal lines. This is drawn at constant temperature T1. This is drawn at constant temperature T2. That is, along this line, pressure and volume varies accordingly to keep this PV equal to RT equation valid. So these lines are actually PV equal to RT equations, which are actually the equations for rectangular hyperbola. That is xy equal to c. Right? So it takes a form of rectangular hyperbola drawn at a particular temperature. This is the isotherms. For an adiabatic process, as I said earlier, that none of the P, V or T are constants. So therefore, the transition would be from one isotherm to another isotherm. So let's say this one. So this path is a path of an adiabatic process where neither your P, V and T of your final state is equal to the P, V and T of your initial state. That is an adiabatic process. So what we are trying to do? We are trying to find an expression for an adiabatic process, or to establish the relationship between P, V and T for an adiabatic process, or rather we say that we start with the first law of thermodynamics as it's written over there, and we derive at this equations, or find the equations, or for the work done, how much work is done in the system, and etc. Everything. But please understand, this is the what we are considering. Okay, so again we go back to the first law of thermodynamics. Keep this drawing on your copy because I will be referring back to this drawing multiple times. So I will just put it on the right side. I've drawn it on the wrong side. Just draw it on the wrong side. The drawing is very important if you really want to understand an adiabatic process. This is U1, this is U2, this is U3. So this is U1, this is U2 and this is U3. These are the three internal states. The transition is being done. Now I'll introduce some key concepts over here. So what we are interested in the first law of thermodynamics. What does it say? Same again, del U is equal to del Q minus del W. The first law of thermodynamics. So what are your final state? U3 and your initial state is U1. So your du is U3 minus U1. right? So I can always write u3 minus u1. As I said earlier, this is a state function. We can add up the paths to arrive at the final path. So u3 minus u1 can be written as u3 minus u2 plus u2 minus u1. So we have broken the entire change in the internal energy into two steps. This is u1 to u2, u1 to u2. Why I read this, right? The reason behind this is that, see, if I need to, all my formula, which are derived either for a constant pressure, or constant temperature, or constant volume. So if we can break it up in such a way that in one path I have a pressure constant or temperature constant or volume constant, I can calculate the entire first law of thermodynamics, entire parameters from that. So here I have did exactly the same. If you see over here, this is a straight line. So along this line, the volume is constant. And along this line, from 2 to 3, the pressure is constant. So you've broken up at a constant pressure and a constant volume to accommodate, to understand the internal change in energy of the system. So now we'll individually consider these two parts. So ultimately, this is your du, and that equals to del q minus del w, right? This is what you have over here. Now for this entire change in state, let's consider the right hand side first. I've already said that this is a reversible adiabatic process, so del q is 0. So no heat is added or subtracted from the system. So this is 0. What is the work done? See, the work is done from 2 to 3. There is a change in volume at a constant pressure. So the work done is P dV in differential form, or P delta V. Okay. So the work done, the useful work done is P delta V. Whatever has been done over here for 2 to 3, you can see for the entire chain. Now let's say, how will I understand the u3 minus u2 and u2 minus u1? This is the most important part. So just write this equation. Okay. I'll go to wipe this out. Now let's consider the internal change in energy, right? So let's say, now what we have, what are my variables? Along this, my variable is volume and temperature, right? And along this, my variable is volume and temperature, and along this, my variable is pressure and temperature. So if I want to break it up in terms of temperature and volume, I can do that, or you can take it up in any form. But I will consciously choose the temperature and volume as the two parameters for an internal energy, because I have an expression for heat capacities in terms of temperature. Okay. So let's say internal energy is a function of volume and temperature, right? So volume and temperature. So I am considering the change u3 minus u2 and u2 minus u1, the entire process. That is my du, right? So if I take a complete differential here, so du, now this is very, very important. Du is del u del v at constant temperature dt plus del u del t at constant volume dv. This is for your entire path. If you see, for this path, this is your expression. The temperature is varying over here. So del u del v at a constant temperature dt and del u del t at a constant volume dv. Now look at this equation, del U del V at constant temperature. Okay,